Here in question 3, they give you a graph of f, and if you look closely at it, there's one quarter circle, which they actually mention in the question, and then the rest of the pieces are line segments. They are linear. That means that if we have to find area between the graph and the curve, we can use geometry formulas. We could split that into known shapes like triangles, semicircles, or quarter circles, and use formulas for that. So we've got this function f. We're on an interval from -5 to, here, something important to notice here, -5 to c. They don't tell you what that right endpoint is. They just tell you it's a c value, that it's greater than 0, and that the function f touches the x-axis at x equals c. F of c equals 0. All right, so the radius of that quarter circle is 2. That's going to be important if we try to find area here, but we'll get to that. Let's zoom in on part A. The average rate of change of f on the interval from -5 to 0. Guys, you should know that wording, average rate of change. As soon as you see that phrase, think slope of the secant line. So I'm just going to set up a secant line on the interval from -5 to 0. So that'll be f of 0 minus f of -5 over 0 minus -5. I could read those y values right out of the table, right off the graph, and I wind up with 2 over 5. Fairly straightforward. Moving on to part B. Now on the interval from -5 to c, they're defining a new function, g of x, which is a definite integral, this time starting at -1 to x of f of t, and we have to find the x-coordinate of each point of inflection. All right, well, to find points of inflection, you really have 3 possibilities. There's one for the parent function, one for the first derivative, one for the second derivative, and they basically look like this. A point of inflection occurs where the parent function changes concavity, so if they tell you that explicitly somewhere in the question, you could use that. Where the first derivative changes direction, goes from going up, increasing, to decreasing, or vice versa, or where the second derivative changes sign. Now, a lot of times students will just focus in on that second derivative changing sign, but it's just as effective to look at one of these other 2 things. And the second one here is the one we're going to look at, where the first derivative changes direction, because the first derivative of g, when you differentiate an integral like that, is the integrand evaluated at the upper limit times the derivative of the upper limit. In this case, g prime of x will equal f of x. And since we have the graph of f, it's real easy to see where it changes from decreasing to increasing or increasing to decreasing. So we're going to zoom in on that. By the way, that is the second part of the fundamental theorem of calculus that allows you to take the derivative of a function that's defined with a definite integral. All right, so like I said, g prime of x is equal to f of x. We'll just look at the table. It looks like it switches from decreasing to increasing at x equals -3, and from increasing to decreasing at x equals 0. You write a little sentence there, and you give a justification. And saying f changes direction at those x values, as long as you have g prime of x equals f of x, you're good to go. Full credit for part B. On to part C. Find the value of c now. We have to solve for this value for which the average value, not average rate of change, average value of f over the interval from -5 to c is 1/2. So they're telling you the average value. You have to remember the average value formula, and that's the 1 over b minus a times the definite integral from a to b of f of x dx. Well, our interval here is from -5 to c, so that's going to be the b minus a, c minus -5, or c plus 5, and -5 will be my lower limit of integration, and c will be my upper limit of integration. So let me trade those out, and I know that's going to be equal to 1/2. So now think about what's going on here. When you integrate f, you're finding the area between f and the x-axis, right? That's what that integral represents. So here's where the geometry formulas come in. Let's just go one at a time. Starting from -5 to -3, we've got that quarter circle. Then from -3 to -2, we have that green triangle. From -2 to 0, that yellow shaded triangle. And from 0 to C, that red one. And I've highlighted the areas of each of those things where the definite integral was in the formula. I still have the 1 over C plus 5, but now those things make up the collective areas. And remember, when you're integrating to the right, the bases of your approximating rectangles are positive, and if the graph is below the x-axis, the heights are negative. So that's why we wind up with a negative pi and a -1. And the yellow and the red ones are positive because our graph is above the x-axis there. So let me clean up what's in the parentheses there and multiply by the 1 over C plus 5. That's equal to 1 over 2. I didn't do the cross multiplying and the solving for C here. You can do that on your own. It's C to the first power. It's a fairly easy thing to do. If you have questions about it, you certainly can ask me, but take a look at that proportion that we wound up with, and we wind up with a value of C equals 3 plus pi. And once again, you want to, of course, use the words of the question. So I'm going to erase some of this stuff and just use the wording of the question to answer. The value of C, for which the average value of f over that interval is 1/2, is C equals 3 plus pi. All right, on to part D. It says, assume C is greater than 3, then the function h is defined by h of x equals f of 1/2 x, or x over 2, and they want h prime of 6 in terms of C. All right, well, h prime here, I'm just going to use the chain rule. So if I do that, I'm going to get 1/2 times f prime of x over 2. All right, that's just chain rule. And then, in this case, if I'm looking for h prime of 6, I replace x with 6. So f prime of 6 over 2 is the same as f prime of 3. So f prime of 3, they said assume C is greater than 3, so 3 is going to be between 0 and C. That means that f prime of 3 is the slope of that linear piece that goes from y equals 2 down to C. All right? And that's a fairly easy thing to work out there. They tell us, in this case, that the h prime of 6, when we do all of this, when we multiply that out, I get f prime of 3 there, which is, if I just do the slope, change in y over change in x, I get -2 over c. So I am multiplying 1/2 times -2 over c, and that gives me -1 over c. So there's h prime of 6 in terms of c. There's question 3. And we're going to stop there, and we'll go on to the next question in the next video.